Following on from episode Null, let's return to our surreal window. As truly magnificent as Conway's numbers, or the surreals, are, would you believe that they don't actually capture all of the numbers? And no, I'm not talking about impossibly complete notions of absolute infinity. That alluring game of Cantor's was shown quite convincingly to be truly endless by Conway. However, a whiff of this game is still captured, in a sense, by the proper class of the surreals, the conventional shorthand for which is written no. They seem to eternally pine for this bottomless tower of turtles. So what does it all mean for physics? In what sense could an infinite abyss actually exist? Undoubtedly, our minds contemplate such things to varying degrees. Physicists readily employ infinities, at least as infinitesimals in smooth and continuous fields. Yet Conway wrote in delighted undertones, and all caps, about the impropriety of the surreal gaps. We will literally cover their gaps in an upcoming episode, or attempt as much anyway. Puns, as always, intended. However, in this episode we turn our attention to some well-established numbers that are not properly captured within the proper surreals, or their eternal gaps, no matter how many mind-melting infinities of birthdays we imagine they unroll. First, to recap, in episode Null we saw that Conway's surreal numbers build out all games of orderly freedoms, which unfold in an orderly manner between two players, left and right. These might as well be physically understood as frames of reference. As their number games unfold, the players look like opposing forces of directionality, creating a new numerical frame of reference. Together they build a beautiful structure between them, mutually extending their measure of the unit 1 from the origin at 0, branching towards and away from one another into the simplest, most familiar numbers, towards infinitesimals and infinities we previously defined using our ordinal omega notation, unrolling infinite numerical universes. But don't mistake the structure for space necessarily. We discussed the most natural and physically immediate interpretation of this progression as dependency, or time. These games, created in playful relationship, might appear to build out in increasingly many directions, at least in this abstract sense as graphed. But the birthdays roll on in total order temporally. This two-dimensional sense of space versus time plotted can merely be a tool to analyze the dependencies amidst the numbers, from simplest to complicated. Conway celebrated their birthdays, recursively unfolding from the humblest of beginnings, namely the empty set, and simply structured self-play. What defines its game is what defines the rest, a simple rule of order. Even as complication grows, this one apophatic rule means all surreal structure maintains one well-ordered numerical dimension, reinforced by an eternity of eternities, of ordinal births, out to boundless limits. When we project this structure of dependence into the more familiar number line, we see how the reals and their infinite extensions uncountably grow into their infinite gaps. Hence, in time, they build out a singular, measurable, totally ordered dimension with both positive and negative directions navigable therein. But what about more than one dimension? More? Oh, no. The one rule of Conway's numerical game of games is order. Higher dimensions famously lack order between themselves, or, well, what mathematicians call total order anyway. But, you say, you're simply a physicist who wants, no, needs to describe a world that appears to persist in at least 3 spatial dimensions, and time as well, supposedly, as much as you dream of reversing time or escaping it altogether. You'd really like some useful numbers for this. Oh, well, in that case, you're told, this was solved a long time ago. Simply repeat your number pattern for each dimension you need to numerically describe. Bring them together for one representation of your 3D thing. Calculate to your heart's content with whatever physical laws you come up with. Make your good enough predictions. Squeeze it all onto a coffee mug and call it a day. You know these. Maybe you fear them, maybe you can't get enough of them. If a collection of possibly different types, they are tuples. But when we declare each number to be of the same type, they are vectors, like this vector for 3D space. More generally, they are tensors. A tensor of rank 1 is simply a vector, just as a tensor of rank 0 is a scalar. For instance, one of our surreal numbers, or any of its more familiar flavored resonant numbers living within it. All right, but still, as beautiful as these numbers are dancing side by side in these surreal panels, are we going to regret this decision to instantiate multiple panels of possibly the same exact numbers that we recombine into what we're calling a vector? I mean, it's great. It can represent a point with a direction for some space, or pretty much any space, or anything we want, whatever we declare it to mean. But might this all cause some conflicts at some point? Let's say, as someone quite familiar with machine learning, I know shortcuts have a way of producing unintended consequences, and I get it. Also, as someone raised on vectors, this might all sound silly, but these actually turn out to be legitimate concerns. Vectors do produce problems, not only in theory and foundations, but in real-world applications as well. Ever heard of gimbal lock? The Navier-Stokes existence and smoothness problem? Yeah, it turns out fluids can get around the point of a corner just fine. Well, if vectors are such problems, then why, oh why, could we have based so much of math and physics and engineering on them? To be fair, they work very well in the vast majority of cases, and they didn't just pop out of nowhere. There was an old debate on vectors. Well, old depending on what you think of the 19th century, which a mathematician named William Clifford largely and beautifully resolved. His points are surprisingly underappreciated, at least on the physics and engineering side of things. To start to unpack all of this, let's look at these panels again. Ask yourself, what, if anything, connects them? Nothing is between them. Oh, the empty set. Hello again. If we believe, for our well-foundedness in the surreals, and any conception of numbers building up from nothing, not only the surreals, search on von Neumann universes and Zermelo-Fraenkel set theory. If we believe in one and only one empty set for the sake of what we call well-founded numbers, then the void must be shared amongst these panels, somehow, simultaneously at play, all around and amongst them, building the number children who arrive each birthday. Somehow, an infinite amount of time must pass for the infinitesimals needed for calculus, moment after moment. But we already suspected those were unphysical tools. Leibniz and Newton did anyway. So if the void is shared throughout, even if we make vector components out of nice and simple finite surreal numbers, is time somehow also shared amongst them too? Ooh, good question. Maybe these panels aren't so separate after all. Uh-oh. How then do we have 3, or however many instances of 0? Yikes. Or any of these many numbers that are supposed to be uniquely defined, meaning the answer is not anywhere or everywhere, but uniquely here. This seems like one of those foundational problems where we come up with something to say about it, to get on with life and work and sleep, something worth just a handful of people worrying over it, perhaps scribbling away behind dusty stacks in an old tower, certainly not practically minded physicists or engineers with their sleeves rolled up. Well, what seems like an obscure definition problem for philosophers of mathematics has a way of sneaking up on all of us as a source of serious bugs in physical equations and computer code, even in art forms and the most pragmatic of applied use cases, maybe where it's possible to ignore them to an extent, but still. We're talking pretty fundamental things like measurement, understanding basic coherent structure of any substance, pretty important stuff for nearly any use, not just quantum computing and turbulence, although some problem areas are more obvious in certain applications than others. We're fine with our calculus, quite circularly, where infinitesimals and disjointed analyses work, but we struggle with the corners. However, it turns out our problems began back before any whiff of omega, large or small, back to simple old 0. When we create countable, measurable quantities starting from the left and right personas of the empty set at play, there should be uniquely 1, 0 that numbers manifest from for a given frame of reference. And no, we're not talking about all frames. There could be any number of instances of frames, each with their own 0. This is not about one universal surreal window or tree to rule them all. After all, these numbers got their start from two relative perspectives of the empty set, not some preferred basis. Hopefully it's becoming increasingly clear, not only is time inextricable yet relativistic in the surreals, it is quantized. At least until day omega, but we suspect omegas may manifest mostly as thoughts. Still, even imagining any number of limited or unlimited frames floating around, we need each relative frame to remain internally coherent for long enough to make at least one well-defined measurement by some other frame, or else it might as well not exist. If nothing can remain coherent, then all bets are off on this whole math and physics thing. We might as well swirl off into independent and chaotic oblivion. Wait, that's an option. The point is, we can't have more than one numerical origin in a single frame of reference, no matter how isolated in nothingness it is. This will lead to confused nonsense, both internally for some frame and externally to itself, meaning it might as well meld back into the nothingness from whence it came. So for a single vector, which needs an origin, we technically have not one but three. What is it then that ensures vectors make sense, that they mostly work? How do quantities that live in 2 and greater dimensions keep from breaking the system meant to define them before they even get off the ground? Well, you know by now, the empty set is never done playing games. Our old friend -1, we're finally back to you. It took long enough. As a game move, you mean go back one with respect to whatever positive direction and unit was established. In Conway's convention, like many great mathematicians before him, -1 points leftward to oppose the rightward forward, meaning in games, it's what right will play to approach the endgame, or 0. In numbers, such as in the traditional number line for those who read left to right, the convention is to name them where they take us out to, so -1 is left of 0. But positive and negative could just as easily have been the other way around. This is why 1 and -1 are born true twins with the same exact birthday, the day after 0 is born. Physicists and mathematicians alike perk up for such declarations of symmetry. Connections of these ideas to group theory await further unfolding across a number of future videos, including connections to Noether's brilliance on conservation and symmetry applied to the physical universe. First, we have simpler ideas yet to examine, like what precisely to do about these so-called vector problems we inherited. And our first question, what blasted numbers could possibly be missing from the surreals? To get there, and to get anywhere, from the simplest of number games to the most complicated, we have to understand, or decide, how to get there. How should we get to -1? Oh, easy, you say. Subtract 1 from 0. In fact, this works for any negative number. Just subtract 1, or whatever option you have available to you until you get there. Okay, let's see what that looks like in the surreals. Remember our number game construction where x is a number if its left and right sets follow the rule of order, meaning no element of the left set is greater than or equal to any element of the right. Greater than or equal to is recursively defined by each element, or most importantly, the nearest element of each side rather, holding to what we define as not less than or equal to. So for x plus y, left x plus y and x plus left y / right x plus y and x plus right y define our addition. This, by the way, is a nice alternative to Russell and Whitehead's Principia Mathematica, which proves 1 + 1 = 2 on page 379 before defining addition. See Up and Adam's excellent video on this in the description. Rather, Conway's book on numbers and games has the proof for 1 + 1 = 2 on page 9. Actually, everything you need for it, including the construction and definition for addition we just went through, is only on the second and third page of the text, and the specific example of 1 + 1 = 2 is in the fifth, and it's quite readable. Okay, this is nice. We like the property of the surreal numbers that their definitions are inextricable with their functions. We might say that they are defined operatively. But what if I get really mean and drop you into a world where you can no longer rely on addition nor subtraction, of course, to get wherever you need to go? Actually, I'm not being mean. It turns out this is our universe and how it seems to work, most noticeably for particles moving close to the speed of light. But it appears to be true for everything. Movements, meaning the transformation of coordinates from any frame of reference, require multiplication operators rather than just simply addition. In the technical jargon, this is our well-tested realization to employ Lorentz transformations rather than the old Galilean transformations. Lorentz transformations reduce to the latter when movements are slow. Actually, many multiplicative transformations work, and none may be preferred. A factor of the speed of light is a common thread. This appears to be invariably true for all of our laws of physics and their invariant symmetries. Multiplication is trickier than you might at first suspect in the surreals. A naive attempt actually ends up with what seems suspiciously like addition. See how our learned intuition for multiplication rules as simple foils leads us to think xy might simply be left x times y and x times left y / right x times y and x times right y. This turns out to define the same function of addition from earlier. And look again, it wouldn't work anyway for negative numbers as we intuit it should. In fact, we rely on addition and subtraction to be defined already to arrive at multiplication and its inverse function on a given number. To multiply surreals, Conway teaches us to take left x y plus x left y minus left x left y and right x y plus x right y minus right x right y / left x y plus x right y minus left x right y and right x y plus x left y minus right x left y. Now that is a mouthful, so pause and even try to scribble through some small number examples. It is a bit complicated compared to addition, but still, you'll see with contemplation it appears to be the simplest possible definition consistent with its intended properties. Conway doesn't shy away from the importance of definition and intuition here, nor does he hide that everything surreal is based on induction. No basis is needed when everything rolls back to the non-existent members of the empty set. Just a few simplest of definitions, including that one rule of order. If the surreal mechanics of multiplication still seem mysterious, what we unfold in coming episodes quite literally will hopefully clarify matters. Beyond foundational movements of particles and all scales and flavors of physics, multiplication is everywhere in nature. Our minds, too, as we predict growth and grow ourselves, especially ubiquitous, are the products of the same numbers acting on themselves. The literal heart of this special square play is the square root. A number multiplied by itself is, of course, the root of that resulting product. So what multiplied by itself gets us to -1? Well, obviously it isn't 1 or -1 or actually anything here. Not a single number in the entire enormous, gigantic, boundless window of surreals multiplied by itself gets us to negative. So how will we get there? In a world of exponential growth, in a universe under multiplicative transformations, what gets me backwards? Don't forget, backwards is a relative direction, framed by the player we have perhaps unfairly preferred all along. Backwards might as well be called other forward. And further to the self-acting power of square roots, Knowing the square root of -1 unlocks the mystery to the square root of any negative number, including any negative we can build in our ever-extending surreal window. Since this -1 problem kept creeping up on us, we naturally found the solution. Already excellent videos exist on this history, which I'll link to in the description. As the story typically goes, around about now, the mathematical protagonist arrives at the ingenious, miraculous idea described more often than not as the invention of a new number called I, which they assign to define the square root of -1. An ingenious invention? Or was it an observant discovery? Can something be so true that it is both? Is this imaginary I any more made up than the real numbers that we come up with? All of those uncountably many real numbers, including that very first number that comes after 0. What was it again? More fairly now, is this imaginary I any less real than the natural numbers, even just a small and easily countable finite set of them? It turns out I seems very real and quite natural in our physical world. Electromagnetic circuits and thus computers would not work without I-ness. Oh, well, humans invented circuits and computers, right? Our made-up math, parades, and our made-up inventions. Well, no, we cannot physically build something unless nature approves of the imagined structure. This is how we fail, sometimes spectacularly. It turns out nature has a way, and we must understand this way to get along. It turns out nature seems picky about math. Despite our insistent assumptions of uncountable infinities, no evidence shows any fully captured infinity of any cardinality. Only practically uncountable counts. Picky nature. Limiting our memory, bounding our instantiating energies with some of its greatest hits like the speed of light, Planck time, and other Planck scale measures, exclusion and uncertainty principles. We are working our way towards understanding all of these on surreal terms in good time, because picky nature. But not about I. It turns out nature also needs to have something functionally or operationally act on itself, and as a result, go back with respect to some forward, different forward. Light emitted from the other side of the universe from long before humans existed seems to require imaginary operations to propagate amongst many other quantum phenomena. Why else do you think physicists keep sneaking I into their equations like it's no big deal? Hey, let's start placing some bets now. Even though we have a lot of unpacking still to do before the formal take, let's bet on what is invented and what is discovered. I'll go first. Maybe infinite math is invented, like everything in the surreal window from Omega on. Like a true and perfect third. It's not as ridiculous as it sounds. And also formalisms like the continuous wave function as ingredients to the Schrödinger equation. Perhaps useful hacks on the way to better approximations of nature's beauty, but still not nature itself. However, the strange yet playful mechanics of quanta as inescapable discoverable realities must have some finite and implementable instantiation, as they unmistakably instantiate everywhere. In a sense, every number we imagine is a dance with infinity, yet still, I bet our first tier of the surreal window can play an implementation of the universe beyond our minds, right up to the bleeding dynamic edge of Omega. But are there any other discovery contenders? Inevitably persistent in the signals that nature inundates us with is that the smallest quantum level observations make no sense without a very impactful, dare I say very real, square root of -1. If that statement turns out to be wrong somehow, after millions of well-conducted observations and experiments point to its almost certain veracity, sure, I guess I was invented. But I'm going to bet all my infinitely deep pockets of spherical cows on I being a true discovery in the way that only math can claim. And yes, I just said that as a physicist. So why isn't I captured by the surreals? Well, I must leave you hanging on this cliff for the next episode. This one, or 0, has been long enough. we've teed up Conway's deployment of an infamous choice to introduce no I, a strange mathematical creature where I floats ethereally along with the surreals. No, not exactly capturing I, but rather taunted by it, dependent on it for algebraic closure and analysis, taunting us. Stay tuned as our story gets increasingly complex.